Hello, thank you for coming. This is the third Atlas lecture for 2024, and I will briefly introduce the speaker, Dr. Aris Leontaritis, who initially studied mechanical engineering at the National Technical University of Athens, and his research path in the mountains initiated with the interdisciplinary master's program called Environment and Development of Mountainous Regions of the DUA in Metsovo, in the heart of the Pindus Mountains. The combination of a keen hiker and an ambitious scholar, resulted in a PhD dissertation in glacial geomorphology in 2019. And his research focus is the Quaternary, glacial history, and the paleoclimate in Eastern Mediterranean. Dr. Leontaritis, the floor is yours.
Thank you. So, thank you for the invitation for the Atlas seminar. Thank you for coming. So today's talk, although we are in the School of Archaeology, is not directly related to archaeology, but I think in a way it's also interesting for archaeologists. So what we are going to talk about is the evolution of landscape from glaciers. So we will see glaciers as an erosional force and also as a record of paleoclimate. So as paleoclimate is at millennial scale, the landscape evolution will be at a millennial scale and not at hundreds of years whole scale and so on. So we will start with some very basic definitions so that we know we're talking about the same thing. So what is a glacier? So a glacier forms when we have the accumulation of snow. So in reality, what we care about, and this has to do also with the climate, is that snow survives through the summer period and it accumulates, and slowly, as you can see here, snow turns into ice. This takes some years, this process. So at first we have snow with about 90% of air inside. This is a typical snowflake. Then granular ice with about 50% of air. Then we have firn, which is something between ice and snow. And then finally we have glacial ice with about 20% of air in the form of air bubbles. So also these air bubbles that are trapped in there have provide information about the climate of the past. So the snow accumulates in this zone, which is called the accumulation zone, and gradually as it becomes thicker and thicker and heavier, it starts to flow because of gravity. So if you want to imagine the movement of ice, it's like a very thick honey. It's like dropping very thick honey, and also because of the enormous pressures, it becomes plastic. It's not solid anymore, so it starts flowing. So a characteristic of glaciers, for the definition of a glacier, is to have movement. So static fields, snow fields, ice fields, or like in caves or whatever, are not considered glaciers. And of course, since they are not moving, they are not eroding, because whatever moves causes erosion. And here we have huge masses that it's actually maybe the most powerful force of erosion on the Earth. And so because we have erosion, we also have deposition, because all of this material is then deposited. So this is what a glacier looks like. This is a glacier from Iceland. And let's take a look of what is going on in there, so below the surface of the ice. So here we have the birthplace of the glacier. We have the accumulation of snow, then it starts flowing downwards at lower elevations or towards the sea, depending on the setting. So as you can see here, we have debris, we have rocks and pebbles and sands, and all this creates friction between the movement of the ice and the bedrock. So friction causes further erosion, and it's very typical to have these U-shaped valleys, as you can see here in the section. I will show you also later. And all this material that gets broken, gets eroded by the glacier, ends up either at the sides of the glacier or at the end. I will also show you later. And then this is how we get the characteristic landforms. So this is, let's say, about, since we talk about landscape evolution, this is, let's say, how an unglaciated mountainous landscape looks like. We have V-shaped valleys from the erosion of water, and then all these depressions and valleys and hollows get filled with snow, and that gradually turns into ice. It starts to flow, and so here we have some typical erosional features after the glaciers. So after the glaciers have retreated, because now we're talking about former glaciers that do not exist anymore, and this is like what we call the relic landscape, what is inherited from the action of glaciers. So why do we care about glaciers? What are the research questions that arise from these depositional landforms is, when did these glaciers form, how they are related to regional or local climatic changes, the paleoclimate, and also the ecology of the region, which is of course directly connected with archaeology. So when we say, when did these glaciers form, I guess you've all heard that climate is not constant, so the climate is something variable. And for example, in these diagrams here, you just see only the last 500,000 years. Here we have some ice cores from the poles, and this is how the ice volume has developed through the last 500,000 years. So as you can see, we have at least 1, 2, 3, 4, 5 peaks of glaciation. And what happens is when we have, so where does water come from? From the ocean. So when water is evaporated from the ocean, it gets, this is how Europe looked like about 25,000 years ago. So the ice gets accumulated in ice sheets. So since there is more and more accumulation there, the sea level drops, and this is how it looked like. And you see how Britain was connected with what is today continental Europe. So it was about 130 meters lower than today, the sea level. And this red line shows the fluctuation of the sea level. So when we're talking about quaternary glaciations, we would like to know, like, in which of these known glacial periods did the glaciers form, or if they formed in another period, and then it's also very interesting. If anybody's interested about further information about how we know that these glacial periods existed, we can discuss it. Yeah, so just to get a feeling of how strong is the erosion of glaciers. Here's these are the Alps. Here is a glacier that is still alive. So you see here it's the accumulation zone, and then it starts flowing downwards. So this is a very narrow part. I think it's this part here. And imagine that all these pathways that you see, all these little worm-shaped valleys, they are carved by glaciers, mainly in the last ice age. Let's say in the last 500,000 years ago, 500,000 years, all these materials has been carved by glaciers. So it's about half of the massives, half of the rocks is missing because of glaciers. And all this material that has been eroded, it has been deposited in several ways, and this is what we are looking for. So now some historical stuff about the glacial theory. As in many fields in science, it had to, it was controversy between the church and the science. So we had this prevailing cataclysm theory, the big flood, so that God punished humans and so on. So the first scientists, the first geographers that started to develop a theory, saying, like, there used to be what the glacial theory says, this very simple thing that at times in the past the climate was colder and we had more extensive glaciers. So the first thing that sparked the theory was that they were finding these, we call them erratic boulders. So these erratic boulders, erratic because they're wandering, and wandering because their lithology, their rock, the rock type is different to the one that they have been deposited on. And this, especially in the Alps, they could find these, like 300 kilometers away from the source. So you could have granite, for example, at the higher part of the mountains, and then in other places that there was no, the nearest source of granite was 300 kilometers away. So they were like, how did these big boulders were transported? So there was a big flood theory, and then they were like, no, it was the glaciers. So there was this thing that got the theory about 100 years to get accepted. So this is today accepted. We know that there used to be colder climates, and glaciers are recognized as major forces of erosion. And another historical thing, this is the historical place for the development of the glacial theory. So what you see here is what we call glacially molded bedrock. So this is, the glacier works like a huge sandpaper, and all the material that is being carried by the glacier, this abrasive material, all the rocks, the sands, they polish the surface and they create these striations. So when they found this is in the coast of northern Scotland, and they were like, this has been made by glaciers. They could find similar landforms in glaciers that were alive, they were active, and they figured out that the ice sheets were much larger, that the whole of Britain was glaciated, and it would go further into the sea. So this is how, for example, this is in the Pyrenees, and this is a glacier that retreated just 50 years ago or so. So this is how it looks like. And so they found this in the mountains, and then they found this in the coast, and this is also an important place. So that's for the history of the glacial theory. So some basic now for how the erosional forces create the depositional forms. And this is a wonderful moraine. So what we call this deposited material moraines. And you have to imagine that glacier works like a huge bulldozer. So if you imagine the same process is like dragging your boot on sand, so it would leave a similar mark. I think it's pretty obvious from the sketches of how it works. So you see this is also a recently retreated glacier. You can see very well the formation of the moraines and how the material has been deposited by the movement of ice. Moraines are very important, and we use them a lot for glacier reconstructions and the reconstruction of climate. And this is not only in New Zealand or in the Alps. I have some examples from Greece, a couple of examples. This is from Tymphy, from northern Greece. So you can see all these materials. So the glacier was born here, it was moving downwards. And this is the material that was deposited by the activity of glaciers. Another one from Helmos in the Peloponnese. So you can see here the moraine, this is the bedrock, and this is all this material has been deposited by a former glacier. And another, I like this one from the Alps. It's very clear where you see this material that has been deposited by a very recent glacier. Teeth is what we call this unsorted material that is produced by the glaciers, and when it has become a rock, it's teeth. So the main characteristic is that you have big rounded boulders that resemble the activity of water, but they are unsorted. So you have gravels and sands and bigger boulders, kind of rounded or semi-rounded. Often the lithology, like here, you have boulders that have been carried away from a source that is more far away. And here you can also see that here we have the parent bedrock. You see how it's banded trees, and then on top we have the chaotic material of the glacier. This is also from northern Greece. And this is modern Greece. It's a famous clarinet player in the local fiesta in August.
First game.
Yeah. So another erosional feature from glaciers are U-shaped valleys. This picture is also from Greece. It's from Marafa in central Greece. So here, all this valley was filled by a glacier. The movement creates this kind of erosional feature, a U-shaped valley, as we call it. And all this material is deposited debris. And now this picture is taken from a moraine. You can see here. This is a moraine, and it ends up like this. Then we have the cirques. You can say glacial cirque, but when we talk about the cirque, it has a glacial origin. This is from the United States. So it's typical that there are some glacial lakes within the cirque. So because it creates these amphitheatric forms because of the erosion of the walls of the cirques. So this is also in Greece, in Smolikas, in northern Greece, and here we show these hollows that they were filled by snow and ice, and this is also a very interesting site for archaeology, since at lower elevations there were found Paleolithic tools that are dated. Some of them before the last glaciations and some after the last glaciation, so it's an interesting, let's say, collaboration between archaeologists and other disciplines. So, yeah, that's about the glacial cirques, and I will be fast to work about the techniques. So as I told you before, the moraines are a main thing that we use to make the reconstruction of glaciers in vast climate. So what we do is we map these moraines, these glacial features, and we also date them, and the combination of these creates a sequence which is also chronological. So we have the extent of glaciers plus the timing. So we can have a relative reconstruction of climate. And I will show you an example of how we work when we have a glaciated environment, since this is the topic. So this is where I did my PhD research. This is also in northern Greece, in Pindus. The first thing we do is, when we know that there is a region that is interesting, we study the satellite imagery, and then comes the fieldwork. So this is actually, it's not satellite imagery, this is from, it's UAV, it's from a drone, but basically it has the same effect. So here, I hope you can recognize after the previous slides that here we have a cirque, we have the erosion of the walls, and here we have a moraine, and all this material has been deposited by the glaciers. This is another angle, so here you can see that there is a younger moraine, and then here there is an older one, and then there are these lakes that are glacial origin. So here you can see that there are different layers, so we have a sequence. So a first big glacier carved the landscape, then there was another one that changed it again, then there was another one that changed it again, so it's constantly changing. So the first thing is we have a reconnaissance mapping with aerial photographs and satellite imagery. But as always, you cannot, walking in the field gives more information. So in this case, for example, we had these moraines, these glacial deposits that were in lower slopes that were covered by thick forest, so they could only be mapped on the field by walking. So when we gather all this information together, we produce the geomorphological maps. And what we do here is trying to organize all this information. And as I told you, there is this sequence, so we have different deposits from different times. So we make these families of deposits, these groups, these units, as we call them. So we classify them also in different mountains, or in different valleys, or because in a single valley you can have a sequence, but you are trying to correlate in the whole massif or in the whole region. So here, for example, we had we recognized three phases of glaciation. Unit 1 is the oldest one, the most extensive. Unit 2 is way less extensive and younger, and then number 3. So it's not just the position, we call it morphostratigraphic units because it's also the stratigraphy, so the position and also some characteristics like how angular the deposits are and other characteristics. So after we do this and we make these classifications, we're like, okay, now we need to date these phases, so we can have representative samples from the different units. Have the ages, the dating, and then we can proceed with a glacial reconstruction. The dating is, I'm not getting into much detail. So the idea is that when rocks are exposed on the surface of the Earth, so there is a glacier moving and getting all these big rocks from the bedrock. So when the glacier deposits them, they have not been exposed before to the atmosphere. So when they get exposed to the atmosphere, there is what we call the cosmic phase. So these are particles, neutrons, high energy neutrons that they collide with the rock and they initiate some nuclear reactions. So basically what you know is a nuclear bomb, but it doesn't get that bad. So after these collisions, there are produced some atoms, you can see here, for example, the chlorine. So we have these atoms that you cannot find them naturally in the rock if it has not been exposed to this radiation. So let's say if we know the production rate and we know that there are 1,000 atoms of chloride 36 produced per year, and then we measure 10,000 atoms per gram in the rock, and we know that it has been exposed for 10 years. It's not that simple, of course, but this is the idea behind it. So we get the samples, so these are moraines these have been deposited by glaciers, you see here. So what we do is we take the top part of these rocks, we try to have big rocks that we assume that they have not moved since their deposition, so we need a lot of samples to prove that. It's very important to have a dog with you when you do that. So yeah, that you get some good results. And after we get the ages, we have what we call the geochronology. So by using these dates we get from the rocks, the exposure ages, we have to figure out which ones are the most representative. So then we can assume some ages for each glacial phase. So for example, in this case, we have this unit 3 these are not exactly moraines. It proves that there are marginal conditions, so cold and dry, which is also interesting for human occupation and everything. Then we have another one that corresponds to the last glacial phase I showed you before in Europe, which is very, very small for Earth standards. And then there is another one that we have not found its lower limit, so this corresponds to the most extensive one. So this is how you reconstruct the whole thing by just seeing at first some satellite imagery and getting into classification and sequences and the timing and a framework and that includes also the timing. So this is an example of how we work, and this Mount Timfi, it's one of the places in Greece that we have the most advanced studies. There have been several studies, so now we are in a position to say that we have reconstructed the glacial history of Timfi. So here you can see this is the most extensive and old phase, the light blue one, then there is the pink one. So this is about 500,000 years ago, this is about 200,000 years ago, and this is the last glacial phase 20,000 years ago. And we don't find anything younger than 25,000 years ago, and I will show them how we use that. Yeah. So, just to sum up what we know up to now about Greece. The first thing that is important about glacial studies in Greece is that it's at a position where, geographically, where we have other important paleoclimatic records, so we can cross-check what is going on from different disciplines like stream deposits from lakes, or pollen sequences. So we can infer information about the paleoecology. Here we have some great palynologists in the audience, so if you want to learn more about that, how they use the pollen sequence to infer information about the climate of the past. So we also have these records also from seas, marine sediments. So we have a lot of information about paleoclimate, and then we have also the glacial studies. And to sum up, what we do know is that there was a major phase of glaciation 500,000 years ago, another one more restricted about 200,000 years ago, and then there is this family of deposits that is related to the last glacial phase. And there are some controversial reports regarding the Younger Dryas, which is also very, very important for archaeology. And as regards the Holocene, we have some minor things in Olympus that we can disregard them because it's really local and has to do with local topography. So we have 1, 2, 3 phases, plus another one, the Younger Dryas, that does not appear everywhere. And it's a good example of how we use this to get information that I think it's very important for any field in science that has to do with the paleoclimate. So this is a modern precipitation map of Greece. Today, the data that provide this precipitation map, because things are changing, so the last 50, 60 years, we can see that the northwestern Greece is much wetter than eastern Greece and southern Greece. And this is because the prevailing systems come from the northwest, the prevailing systems that bring moisture and precipitation and snow and glaciers, comes from the northwest. But, for example, what we see during this period, the Younger Dryas, 13,000 years ago, this, for those that are not familiar with paleoclimate, is an important period that after the last glacial age, when the climate is warming up and the glaciers are melting, we have a cold spell, a short but very abrupt and intense, at least in Northern Europe, cold phase that we kind of see also in our region as well, in Greece. So what happens is that today we have this precipitation map, right? And so the source of glaciers is, on the one side, is precipitation, so we need snow, and the other thing is temperature. That has to do with how extensive the glacier will be. Some studies about temperature have shown that across Greece, although this might sound a bit weird when we talk about the highlands, temperature has to do mostly with elevation rather than latitude. So if you expect that at 2,000 meters in Crete, you have much warmer temperatures compared to northern Greece, this is not the case. So they are kind of uniform, let's say. We can make this assumption for what we are talking about. So for the Younger Dryas, as I told you, in northern Greece, we don't see anything. There were no glaciers formed during this period, whereas in the Peloponnese, we see glaciers that are also in open space. They are not confined and topographically shaded. And So there is actual the formation of actual glaciers, and we can attribute this to different precipitation patterns compared to today. And I would say it's something like we see in the last 5-6 years if you're into the weather, but now we always have southern winds prevailing and snow, and if you're skiing or anything, you have noticed that indeed there are periods where these mountains here are full of snow and here it's super dry. So, okay, this is a bit, not so simple, but I'm just giving you an idea of how you can use all this data to get information about the climate. And this has to do with the cyclogenesis, the atmospheric circulation in the Mediterranean, and how this is an example from very nice publications, and data showed that systems were coming with a southwestern direction, as you can see here in Greece, and not like this. And that's how you get trying to get the whole picture together. And now just a case study, I will be short. Of an actual, this is a very fresh thing we did in October. So I'm just gonna show you how we work with something like this. I will be very long. So Crete. Crete has two mountain massives that are almost 2,500 meters, and because of their position, this will show you here. You see the precipitation map. You see how much precipitation there is here. So because of their position in Crete, they receive a huge amount of precipitation. Actually, these highlands it's wetter in the Lefkaoi than compared to northern Greece. So we have these high elevation massives who have a lot of precipitation. So we know that these numbers are places, mountains that we know there were places and have been studied. So we want to see the evolution of glacial formations throughout Greece. So the nearest we have is in Taigetos, in southern Peloponnese. And so of course comes the question of like what was going on in Crete. So this is a very interesting topic for us because there are controversial reports from previous studies. Some people said, yeah, there is definitely signs of glaciations in Crete, and other people say, yeah, we did dedicated study and we found nothing there. So, and because it's controversial, there were other places more easy, let's say, to deal with. Crete has been left aside. And the funny thing is that the White Mountains in the west, they are much more extensive, wetter, they are very big, massive compared to Psiloritis, Mount Ida in the center. But we spent several hours in watching, looking at satellite imagery in Athens. There, we walked more than 10 days, nothing. But satellite images revealed very promising location on Psiloritis. This is how it looks like. So this is, like when you're looking at Google Maps. I don't know if it's very obvious for you. So here is the silk, and here is the moraine, and you can see something was flowing here. This is Google Maps. This is Bing Maps. Don't underestimate Bing Maps. I just wanted to mention that because sometimes they have a nice view. And what we were really lucky about is that many times it's very inaccessible to get to these places. But you see this line here on the moraine. This is the way of Psiloritis. You start at Psiloritis, so this is a very wide path. You just park the car here and you walk, which was very convenient. So then the question comes like, how comes that people didn't know about that? And this is a bit of literature review and a bit of detective work. So what happens is that after we found this information, we found a report by Meur, I don't know if I pronounce it right, it's a French guy, about quaternary glaciation on Mount Ida. That was very nice and interesting, but why nobody knew about that is that this remained buried in some shelves in the library of Bordeaux. And it was digitized just some months ago. So we were very lucky that we also got to get this. So it's not that innovative what we found, but yeah, it's a nice combination. So this guy had already reported that in 1985, but he provided no pictures, no location, nothing. So people were like, yeah, it's another guy that said there were glaciers in Crete. So now we have something, and this is a photograph from this 1990 publication here, you can see. But anyway, now it's almost 35 years, huh? Okay. So this is the location map. So this is where this moraine cirque system is, and the red line is what we walked to see if there were other interesting things. So this is the cirque. I think it's very typical from what also you have seen. These people are walking on the moraine. This is the path. You can see here, so this is another moraine. I don't know how obvious it is, but I will show you also later. So this is glacial material. Here it's very obvious. These are some mosaics from aerial pictures from drone. So the scale is not actually correct, but you can see here the path, how it goes up. This is the moraine, so this was filled with ice. Here we have this ice polished bedrock, which is pretty impressive because we don't get to find this very often in Greece because of the limestone lithology and the erosion of limestones. So here's one moraine. Here you can see this is one moraine here, and then there is another one here, and here. And I think also this view. I don't know. I think you can get the perception. So first, so you see the different steps. So we see this, and now it's the time for classifications. This is a single glacier. It's more glaciers. What happened here? So this happened in October. Of course, we don't have any dating results. So from the UAV survey, this is the digital elevation model, but in this case it doesn't provide so much insight because it's clear. So I prefer to work on this than this. So looking at the classification, okay? So the first thing that someone can observe is that this marked with black color, this moraine ridge here, is something distinct from this moraine ridge here. This P1, P2, P3 are the location of these photographs. So this is 1, 2, 3. So looking from below, you can see this is the main moraine ridge here, the black one, and this is another one that is distinct. So we have another glacier that formed this one. So we have 1 and 2. This is from position 2, so this is one moraine ridge, and this is the second one that converges towards the center of the valley. And this is position 1, looking straight down here. So the first thing we find is that there are for sure 2 phases of glaciation, but I do remember this is devoted to archaeologists, so seems to be quite old. But there is also a younger phase. So this is what it looks like when you just go there, and this is when you start to elaborate things. So this is the outer moraine, this is the inner moraine, and these are the youngest moraines. And these are I would say at least LGM of the 25,000 years ago. And then in here they could be also younger, which is very interesting for Crete. We didn't expect to find this. So this is of how, let's say, we can see the evolution of landscape. This is a small valley; it's not something massive, but just to show you the philosophy of how you get all this information. And here we don't have any dating. We have not spent any money. We just get food, a car, water, and you're there. You take some pictures.
And the dog.
And the dog is not here now. Unfortunately, you said you were not.
You didn't have to do something there. That's why.
That's why. Yeah.
So after we found that this is very interesting, we went for sampling without the dog. Now we're in the process of hopefully getting some funding to take this, and we will need more samples, so we will get the dog there. Otherwise, this would be crap.
Not to compromise methodology.
Yeah, and to close, I liked very much this is a competence. I was reading this book from Judith Shalansky, An Inventory of Losses. And I found this part, I was just reading it for fun, and I find it very, very, very to the point with what we are studying, and not only us, but everybody with paleoclimatic records. And yeah, that's all for me.
Thank you.
Thank you.
Thank you very much, Aris. It's very, very intriguing, and at least for me, very helpful talk to understand the process of glacier developments.
Yeah.
Obviously, I've witnessed or understood that there are experts in the room, much more experts than myself as a professional archaeologist. I apologize for my commitments in advance.
No, it's,
But I'm sure there are other questions in the room. Please.
He mentioned, I think, at the very beginning that the oxygen or the air in the air bubbles in the snow capture climate information. How do you analyze this? What kind of information do you get?
for example, CO2 concentration.
So, like,
So
the
you get
older it is, the more
No.
CO2.
It's not necessarily, but you have a bubble of air that is like taking a sample from atmospheric air from the point of that it was trapped in there. So if you date, so you get a core, you date it, and you know that this bubble comes from 500,000 years ago, and then you analyze its composition, and you know different things like CO2, SO2, yeah, particles, I guess. Maybe
If you're
pollen,
lucky.
if you're lucky.
Methane,
Methane, yeah.
So you actually get to know how was the atmosphere at that time period.
Mm-hmm.
It's not a way to, let's say, define how old is this bubble.
No, this is
No, you have to.
the dating is another
Okay.
thing. So, and but what is very nice is how is the definition of go on with your questions and I'll talk about it. It's your favorite one, no?
Which one?
The delta weighting.
Yes. But I wanted to ask something else about the younger Dryas.
Yes.
I think we've talked about this before. You mentioned that the younger Dryas is documented and pinpoint chronologically in Northern Europe and Central Europe, but it's also pinpoint, of course, without glaciation and without glaciers, in the Middle East and the Near East, so with other paleoclimatic evidence and proxies. The question is, how come we don't have it in Greece, pinpoint chronologically, or why maybe it wasn't as abrupt, or, but if we're in the middle and you have it in the east, you have it in the west, and then why can't we pinpoint it here? Okay.
Hello there. It's a good way. I don't know if you want to say something about that.
We can discuss all night about it.
Yeah, we can discuss about it now. But I don't know. I find it very interesting that the thing is that even if we get the glaciers, they are very small, very marginal, so they wouldn't give a signature, a signal in the deposits, like in, I don't know, marine deposits or anything. So, for example, the one I told you about with the Peloponnese, it's a minor thing. It's a huge catchment, and if you analyze the sediments, because they're working on the Corinthian Gulf, and once more, we don't see that, right?
We don't have a temporal resolution at the moment to
Yes, yeah.
see, but you
In the
have to
Lepsina,
take into account that the younger Dryas is a very short
Mhm.
event. So first of all, you have to have the correct record, temporal resolution enough to see, And second, you have to be in an area where the effect is easy to trace. I mean, we can trace the younger dryas event in the pollen records of northern Greece. We can trace it.
Okay.
But we cannot trace it in other records, in bigger basins, in small, depending on where you are, because the terrestrial environments are not one thing. So, depends what you're looking at and how you explain it. In Lake Prespa, for example, it is very evident,
Okay.
extremely evident.
Okay.
In Salami, in Lesbos, it's not.
It's not, yeah.
It's not.
So I think it also has to do with the survival of trees, since we're talking about pollen.
But also for glaciation, it is interesting that you have the youngest phases in the southern Greece rather than in northern Greece.
Yeah,
In paleoclimate terms.
The youngest section.
and now we got some results from Parnassos that I received them like yesterday, so I haven't elaborated them, not yesterday, like a week ago. That, you know, they need some work because right now they're not where they should be, but it seems that we got some very young stuff again in Parnassos.
Very young, meaning 13,000.
Meaning even Holocene age.
Okay.
But very small, very small.
That's really interesting. All this in dates in Parnassos. How far up?
It's pretty, like, always you have to get in mind the local topography. So it's in a very closed, north-looking rock face, you know, like several 100 meters high, so it gets really shaded.
So it can be like a snowfall.
No, it seems like used to be dynamic ice, I think. And so it's once more, it's an evidence that we have a wetter climate in the south. A wetter climate. And what we also find in northern Greece that is also very characteristic is what we call rock glaciers. A rock glacier is actually a glacier, there is ice in there, but it's mostly rocks. So you have a core of ice that it's creeping because of its weight, but it's mainly composed of rocks, and they make some very characteristic formations. In northern Greece we find a lot of these, whereas in southern Greece you don't find these. So rock glaciers are very typical of very cold and dry conditions. So there are these indications, but you know, if you don't get the other records to work with that, you cannot say because we found the rock glaciers that it's that. And, okay, it's very difficult to date the rock glaciers.
And it's a different signal. I mean, here you have the signal of low temperature with humidity. If you don't have humidity, you can have lower temperature, but you don't have a glacier.
Exactly. And this is, we can see that in very severe cold stages when, you know, like you start, it's getting colder and it's still wet, and then because of, you know, like it's the sea temperature drops a lot, there is much less evaporation, there is a lot of water trapped in the ice sheets. The ice sheets are white, they're not like the dark color like the ocean, so they reflect the sun, and all this reduces the amount of water that gets evaporated, so then you get into a very dry period and cold. So then this is not okay for glaciers to survive.
Just speaking, really, excuse my ignorance.
No, go
No
on.
idea. And mostly I deal with, and not even with prehistoric periods, but even I deal with historic periods. So yeah, I'm even further more recent for you guys. But in terms of velocity, so how fast can all this? So we're talking obviously, you know.
We're talking about it varies. It can be from 5 to 40 centimeters a day.
Okay.
But then there are these phenomena. It's called the surging glacier, which is a big problem also in Alaska. It's a thing that they study a lot. They still have not found what triggers that. So surging glaciers, you have a glacier that it goes like an avalanche.
Yeah.
Just like that, it gets triggered, and you have huge amounts of ice flowing and, you know, killing people. And so.
Just very dramatic singular events that are happening, which is, you know, more or less, you know.
Yeah, there are some cases where we know what triggers them, like for example in Iceland, you have these glaciers that sit in volcanoes, the volcano erupts and then of course it melts and then goes
And everything goes
boom like that.
Any further questions or remarks, comments? Well, if that's not the case, then may I just add another one? It's just because I was very much, again, interested more or less in historic periods. You know, but then again, talking about the lower altitude levels. So you were talking about the lakes, the glacial lakes, and the evolving landscapes. I was thinking about not the glacier itself, probably, but all the derivatives of glacial lakes, whatever, landscape formations, whatever, and the use for that for humans as resources, as natural resources, so lakes and everything. What do you study that? Is that interesting, especially in terms of thinking of when humans come into play, when archaeology comes into play?
Look, the thing is that when we're talking about, like for example in Greece, when we talk about glaciers, we're talking about mountains environment. So I would say that the limiting factor for life is not water. I mean, water is available during glacial periods or non-glacial periods. So it could also be, but since glaciers are melting in a way, and we don't have the case where it's flowing to the sea, so we don't really get the fresh water. I think I wouldn't focus so much on that, but what is interesting is to see the vegetation patterns, because for example in the northern Greece they worked a lot on that, and there are places where today they're completely barren, that there used to be tropical forests, or you have these zones, or I think especially for hunters and when you have open lands or close.
Exactly, in Paleolithic areas where ice would melt and then animals will be coming in, and that will be becoming seasonal, temporary hunting grounds. As far as I remember from the region.
So you remember. So then you have seasonality, so it becomes even more complex. But I think it's somehow related with these Neolithic patterns, right?
Well, the reason why archaeologists have been obsessed with the Younger Dryas is that it has been it has been claimed that this abrupt phenomenon of colder weather triggered the Mesolithic hunters, gatherers, and to monitor closely how the cereals were behaving, and by monitoring them very closely, because they were afraid that they would not be as abundant as they were before at the end of the last glacial maximum, they realized how they can regenerate them. So they got entangled into sowing, and then they mutated them. They chose a certain mutation, and so we have the Neolithic package. So it has been, the Younger Dryas, from some scholars, it has been directly related to Neolithization. In Greece, we don't have this, we don't have evidence for the Mesolithic groups coming up with the cultivation of cereals. We believe, most scholars believe that this came with newcomers as a technology, and this could collaborate with evidence of the Younger Dryas not being as severe in Greece, but still there are others who dispute this theory, of course, and there are other theories on why they came to to domesticate the cereals. Yeah. So there are other theories as well, but this is why the Younger Dryas is so important to us.
Talk in terms of climate and vegetation. You cannot compare vegetation in the climatic conditions existing in the Middle East, where all these things and maybe they cause this thing, maybe not, but they coincide with the vegetation and the climate in the Balkan Peninsula.
Exactly. So
It's not comparable.
No, it's not
So
comparable.
it's totally different. You talk about huge, big rivers and deltaic systems and plain deposits of Tigris and Euphrates and so on stuff, and this is not comparable with what we have in terms of landscape in Greece, and in terms of vegetation, and in terms of climate as well.
Yeah, for example, in Crete, they believe that the cereals were not endemic anyway. They were.
Yeah.
They're important.
I don't know about Greece, but
Yes, well, cereals existed, at least in terms of Poland, but we don't know if those are the cereals that became cultivated.
so maybe they were just wild cereals and then they imported
But the vegetation is not the same, the landscape is not the same. What the gatherers were gathering was not the
It
same.
was not the same. So they would not be monitoring these plants. Maybe different.
What's the earliest evidence in Crete for those kinds of cereals, for supposedly imported cereals?
7,000 years.
7,000
So PPNB.
Yeah.
So it's quite late, and Crete is the best example for those who support the immigration theory as to others who support the acculturation. But because you have the Icelandic character of Crete, and we know that it has always been an island, even in the Messinian salinity crisis, we know that they came from the sea. So. And
7,000.
no. And you have a different fauna also,
Sure.
not only flora.
Yeah.
And then it is substituted by the Neolithic fauna, which is broad.
I mean, speaking of islands, I mean, you mentioned it before. I mean, when did England become an island? When was it? Is it
I don't know.
during the last glacial maximum?
Possibly,
at
but
some
it
point,
was
but-
connected with ice sheets, not
Which
with
is
not by
it's
land.
huge. Also, you know, this is why it's so interesting also to collaborate with these things, especially when you're discussing the earliest periods of human evolution.
Exactly. It's a very nice work they did, sorry to interrupt you.
No?
Here there's the Corinthian Gulf,
Yeah.
and you want to tell us a couple of things about this, how it changes from a lake to marine environment and back. So,
Oh, that would be very interesting. Yeah.
Well, it depends. Mostly the climate works on this. You could start, for example, Ellipsis Bay. You know, it used to be a lake back in the salinity crisis, and slowly, because of the change in climate, the water started, the sea level started to rise, and new pathways for the water opened, and then we have the bay that we have today, which is pretty shallow, but it did used to be a lake, and we do have pollen analysis data, right? Yes, and everything. That's pretty much how it works. I mean, what you see is changes in temperature, in climate, and that affects the morphology, the sea level, and it rises. Same happens. Now, when you ask about when Britain became an island, it's a completely different process because it has to do with the isostatic rebound, which is basically when the temperature rises, you have a warmer climate, glaciers melt, so the weight that was deposited on the ground is slowly being lifted, so the ground kind of lifts up.
the
Because
whole
there's no this
place,
pressuring down.
the
That's
whole
how.
place has a boat. So
That's mostly how Scotland, Britain, and Sweden became how we know them today. And that was a period that there was a severe decline for these areas.
But that's for freshwater also. Vienna, they made another study.
The non-filtering cysts.
Yeah.
The same study with Poland.
Highly interesting. No, because it's changing landscapes, changing resources.
Imagine there is a narrow passage that connects the Gulf with the sea, so when the sea level drops, this is isolated, it becomes kind of brackish or a lake, brackish. And then, it changes again, so the sea flows inside and you have this very clear...
Yeah.
So this, it plays a role, but the thing about vegetation is that when you have these big catchments, like the way I perceive it is that there is these tree zones or different vegetation zones, and they move up and down. So when there is space to move up and down, they just keep going.
Yeah.
So the same ecosystems keep going. So I think it's nothing changes for people instead of just just moving a little bit further up and further down, like we do seasonally. Something. This is what I have in mind. And yeah, also like now we were in the north, like just some days ago, in the border of Bulgaria, and you have this special, there is a forest in the north of Greece that it's considered very special and so on, because you can find species that do not exist elsewhere in Greece, that they come from the north. So you have some kind of pine and other species. I don't know in English how it's called. Ismides, what do you say?
Birch.
Birch.
Birch in
Simida.
but it doesn't really exist. So it's a northern thing. So I was thinking of, because this was also glaciated in the past, so it's interesting to see all these forests in there, and why they survived there. I was trying to think. So it's kind of, there were the glaciers. These forests were lower altitudes, and the climate is warming. They go up, and then you have like a little island there that has some microclimate that is colder, so it gives some conditions that allow them to exist. So this, what we call the refugia. So of this moving of, interacting. There is this. It's interesting that we are on this zone where we can see that northern Greece is like this, in southern Greece it's not. So it's really, that's why I mentioned that Crete is important as well. And
Indeed. One question in the back.
I wanted to ask something about the methods. That's when you say you do both of satellites and the field walking. Like, what kind of information can field walking complement to the satellite image methods? And do they provide more detailed microclimates environments? And do you also do selective field walking, or do you do the whole region where you select to study?
Well, it mostly has to do with mapping, and it's many times that you miss things from satellite imagery that they're not visible for different reasons. One, of course, is forest covering, but also just sometimes it's just not obvious. It's the angle or the lighting or whatever. But, okay, if you could have access to many different types of satellite imagery, maybe you could get it, but you would get into that only if you had some first indications that you really want to work there. But like this example in Crete also, that when you see the satellite imagery, and also, for example, this first study from the French guy was, you get the feeling that it's a simple glacial phase, whereas it's not. And this is what makes it important. Otherwise, if you just say it's a quaternary glacier sometime in the past, okay, but yeah. So that's what you get in the field. You get the detail, you get the texture, you get, because this material is not the same depending on its age, depending on if it, like I said before, the rock glacier and everything. You need to get also these, and this is just the basic. Then you cannot go also deeper with sediments, making sections and analyzing the sediments and so on.
Great. There are not any other very last comments or remarks. Then, with one last reference to your last slide, showing that wonderful quote, I think it very nicely shows the call for interdisciplinarity, because as an archaeologist, we also find ourselves, I think, we can identify with that quote.
I'm sure.
Attempts reading the value of the past and etc.
Yeah,
it's something that we can very, very well relate to. Exactly. Attempts to derive conclusions and lessons from the experiences of the past are ample within this record, also within the archaeological record.
Yes.
So thank you very much again for coming today. I've definitely learned a lot. The next lecture is not in April because we're missing the Easter break.
Yes.
It's then in May 17th, I believe.
Yes.
And we have a colleague speaking about a topic pertaining to classical archaeology. Correct? Wolfgang Pilzer, a professor at the University of Copenhagen, dealing with Eastern Mediterranean art and landscapes, Hellenistic and Roman art, dealing with nature and landscape and how that's so. A very different topic from today, but nevertheless, hope to see you there. Thank you very much for coming.
Thank you.
Thank you.